All right, lecture 33, metaprogramming. I think we only have 3 lectures left, and the one that we do this Friday is probably going to be a review for the final. So I wouldn't get too excited about the final. It's going to be multiple choice. I don't think I'm going to make it too hard, so people should do well on it. And it's mostly going to be on how the microcode works and the lectures we've been having over systems software and how the system software works. So it should be fairly straightforward for most people. There's a nice article out there on the web on QEMU, KVM, and virtual machines. I've put a link in it. Please go read it. It explains how these things work together at a system level. It is Linux oriented because KVM is how you do virtualization on the Linux system. And the tools that run on Windows have proprietary stuff in it that you can't really discuss because of licensing with Microsoft, so we don't really know how it works. I think that's the answer. You have to follow the documentation, but under the covers, we have no clue. So let's talk about some metaprogramming. We're going to actually start with Make and other build tools. Make is a very versatile tool that does a particular kind of thing called backwards propagation. But it allows you to take the dependencies that you have for a particular thing and list what those dependencies are, as in the set of inputs. And when you do want to build the output for that, you do some set of commands. If one of the commands fails, then the makefile stops at that point and you can take remedial action to fix whatever the problem is. So, in a certain sense, it's a way to name a collection of little scripts that you're going to run. I certainly use it that way. For instance, I have a makefile that I use to take the markdown files and build them into the PDFs for the class. And it uses some other steps besides what are in here, but this does the big complicated things that have long command lines. And that way, when I change something, hopefully I just type make, it rebuilds stuff, and we're all good to go. Hopefully. Although there have been days when it did not work for this class because I didn't pay attention and there was an error. I was running it in the wrong directory. But usually it works. So the way a makefile works is you have an output, and it depends on some series of inputs. When the inputs, the assumption under the covers is that if you change an input, and the output is older, as in farther back in time, then what you have to do to fix it is you have to do some sort of command line commands. A good example of this is something where you compile a source file into a final executable. And you would expect that the executable would be newer than all the source files. That is the temporal ordering. You shouldn't have it in the other order because that means that the executable is out of date. And most files that you have where there are multiple inputs, this is the way that it works. Now, since these things can be chained together, it's not so much what happens on a single line in the makefile as it is what happens with a whole bunch of different interacting rules. And there is a process called a topological sort that Make actually has built into it to put these in the correct order, so you can have many different levels of things coming together and getting processed into many different kinds of outputs, and it puts it in the right order for all of them. That does have the assumption that you don't have circular dependencies, which is a weird thing, but is sometimes possible. Now, tracking all of these dependencies can be quite tedious sometimes. So there are a variety of tools out there that will help you with the dependencies. For instance, there's things that you can give a C++ program to, and it will go find all of the dependencies for it and build you the section of your makefile that has all of the dependencies, or update the dependencies. But this is way better than trying to have some sort of a script that compiles things ad hoc, especially in a collective system. And lots of systems use Make, like Linux or the Postgres database, and they have thousands of lines of rules on how to take this and build it. Not just build it, but also rules on how you build it for Windows, how you build it for this kind of Linux or that kind of Linux. So these things can be quite complex, and it aids tremendously in rebuilding, because what it tries to do is make the minimum size build to get to the final destination. Now, some systems don't have this built into them. I'm thinking about things like Maven. It's a tool for building Java stuff that never seems to look at, and Eclipse are the two big tools for building Java stuff. They never look at the dates of your .java files, and they want to rebuild all sorts of stuff that I can never understand why they rebuild, and they tend to take a long time. And my example for building Java is that it's not uncommon when I go and build some Java stuff that it takes a half an hour every time I build it. So that's pretty horrible. Now, in a good rebuild for something like Docker, okay, you only have to build the last little piece, and usually it's pretty fast. So you go 1 second for this build, 2 seconds for that, another 1 second, 3 seconds. You know, you're doing pretty good, and finally you get to a spot where you go, and it's lack of a real build system, and there you go. There goes a half an hour while it rebuilds stuff. So some of these things are not so good. The default thing for make is a file called makefile, like so. So if you're building something and you see a makefile, that's what it's there for, is to run through make. You can also specify the makefile on the command line with a -f option. For the Unix, if you're using make on Windows, the one that comes with VS Code, it has different options. It's a /f : the file name you want to run. So let's look at, this is kind of the dependency tree thing, where you have some default rule and it's dependent on dependency 1 and dependency 2, and you've got these listed out as dependency 1 and dependency 2. Let's actually take a look with a C program and see how it works. I've got this makefile, and this makefile is over here in the directory if you want to play with it. It is make1.make, I believe. That is the second version of it. Let me find the first version of it. It's example make. And in this example, what we're going to do is we're going to build a little C program. The C program is inanely simple, but I've split it up into two files so that it's going to get linked together. Linking is the process of taking multiple object files, basically the hex files, except they're written in binary to save space, and sticking them together into a single program. Now, to do this when a linker runs, these things have to be a thing called relocatable. So they all start out at address 0, but it needs to move code around to different addresses. So the linker has to understand how to tweak code to get the correct addresses inside, which is a fairly complicated process most of the time. But a .o file, or in Windows a .obj file, is set up specifically for this, so that it has an index at the beginning for the linker to be able to read, to say these are all the things you've got to change to make this relocate to a new address. So when we compile this, instead of compiling the entire program all at once, we've got AAA and BBB that we're going to compile to object files. And then we're going to take the object files once they're built and build it into this final executable. We can go look at the little simple program. There's the main is in BBB, and you notice it includes AAA, so it has a dependency on that. And if we look at the make file, we'll see that, yeah, it's got that dependency listed there. And this is because I put it into the make file to have the dependency, right? And if we look at AAA, we'll see that, yeah, it has a function. It also has a dependency on the same header file. And whatever it does in here, it does a simple thing. It adds two numbers together. So this is not real exciting code. And it also has this macro that it calls aprint on A and B. And this is not the most outlandishly wonderful example, but it's an example. So here's the macro, and here's the definition of the function. The reason I have to have the definition of the function in here is so that I can call it from the main program. I call it right there on that line. And C, at least in modern versions, wants to have a declaration of every function you call so it can make certain at compile time that you pass the correct set of parameters. So the header file has that in there. And those are the pieces. Now, if I go and make this, if I go and make minus f example.mk, and I'm using a tab completion in the shell, which means I typed make minus f ex, and I just hit tab to complete the file. And it says, oh, all I had to do to make this is just the final step, because the object files were already there. Now, there's a command in Unix that I stumbled over when I was first learning how to use Unix in the command line, back in the dark ages when there was only 3 channels on television. And I mused for the longest time why anyone would ever build a command like this. It just seemed like the most inane thing. It's called touch. And touch updates the timestamp on a file without changing it to the current time. So you can just touch a file and get it to the current timestamp. So if I use touch, and I just touch the input file for here. Now let's see what we do with make. Okay. I'll go back to the make command by going back in my history. And you notice now it says, oh, the source code changed, which means I've got to rebuild the object file for this. And then I've got to take the 2 object files and combine them into the final executable BBB. So there's the pieces inside a make file for combining things together and making them into a single executable. Now, with stuff that is source code, in a command line environment, you can make all sorts of things. You're not restricted to just compiling stuff. For instance, documents. Let's say you're using LaTeX to format a document, but it's also got some macros in it that you've defined. So you may macro process it through a macro processor, do some other things, and then run it through LaTeX and then TeX to finally get a PDF of a file. So there may be multiple steps, and make is used in all sorts of contexts outside of just compiling code. But it is an incredibly useful tool. Let's see what happens when you have an error. Let's go put an error into this code. And see what happens if I have an error in the code. Let's put in, okay. Let's just add something right there. Now this won't compile. So if I go and I do make, there we go. So it ran the compiler and it showed me I had an error, and you notice that make stopped. Okay, it didn't continue on to try to link something that isn't going to work. So whenever you have an error reported by something, provided that the program works well in the Unix environment and returns an error status, and you're using it in make, it will stop at that point and it will not continue to the next command. Now if I fix my error and go back and do make, then you see that it's fixed, and now it goes on and it does the second command that links it. So make has lots of capabilities for doing a rudimentary level of error checking. It's also good for a lot of things like building tests for integration test if you're doing an API test, because each test in the API, you can run a test, and in the make file, if your test says there's an error, you can stop at that point and not continue to run hundreds of other tests. So it's got lots and lots of utility cases. Notice I also said it does backwards chaining. It's actually a programming language. Now, with all of these capabilities and these rules, it can be quite, it's annoying to have to put in every line for the make file. So if we look at the default rules, you'll notice here, I haven't put in the rules for how to compile some of this stuff. These C files that just have headers, I just listed out what the dependencies were. There are default rules in make for building all sorts of stuff. And make is extensive. You can create your own default rules that say whenever you're going to a .o file from a .c file, I want you to use this kind of a rule. So if you go looking up in make how to do things, you can extend it to all sorts of new languages that you've never seen before. for instance, you might have some extension nobody uses, like a .m2. And you might want to say in your makefile, oh, whenever you see a .m2 going to a .hex, what you really want to do is you want to go run this specific command with these options and substitute it in. So then you just have a makefile, and when you want to reassemble whatever this M2 file is, you just type make and it assembles it with the correct options. And you don't have to go back to it a bunch of times to go, now, what was that last option that I had to put on there to get it to upload? And did I type it in right? So these kind of build systems are tremendously useful. It's not the only kind of build systems that are out there these days. There's a very common one for doing JavaScript called Webpack. Webpack requires that you write a program to actually build your stuff. I suppose in some sort of a way make is a program. But the program in Webpack is a JavaScript program, and you can extend Webpack with all sorts of fun things for building and assembling your program, but it doesn't have a dependency checker in it. So every time it goes off and does stuff, it wants to rebuild everything in your entire web application. And it has some other features that are actually pretty useful, but it really irritates me every time I'm standing there looking at my computer going, I changed a comment in one file in 100,000 lines of code, and I'm standing here for 3 minutes waiting for Webpack to get done so that I can test this file again. And those kind of things happen. There is Ant, which is a common build system for Java. Again, it doesn't have a dependency checker, although there are third-party dependency checkers that you can add to Ant. Again, you have to write a Java program to build stuff. An example of somebody that got it right is Go. Go has a built-in dependency checker that keeps track of the dependencies on all of your files for you. And when you do Go on a program, it's usually really, really fast. You can recompile 1 million lines of Go code and have it linked and ready to run usually in under 2 seconds. And the way it does this is because it keeps all of those files that you have built, plus their dependencies, plus all of their object code, and a partially linked copy of your program ready for you to relink it and just modify the piece that changed on the fly, ready to go all the time. So whenever you run Go, it's always fast. And I like 2 seconds much better than I like, half an hour or an hour, or, oh, I'm going to recompile my Java program. I guess maybe it's time for a lunch break. And then I come back and I go, oh, damn, there was a syntax error. I left out a comma. I guess it's time for a second lunch break. And then you go, oh, no, I put the comma in the wrong place. It's time for it. No. I'm looking at my watch. And yes, it is time to go home. And all you did is 2 commas. So a good dependency system that does this is a really valuable thing in terms of productivity. And when I say 1 million lines in under 2 seconds, you can recompile lots of Go programs in less than half a second. So it's almost instantaneous. It's a marvelous thing that works that way.